Hi, I'm Ben-Yaakov. This presentation is entitled Converting Buck-to-Buck Boost to Get a Negative Voltage. I'm showing here the generic representation of a buck and a buck boost. In the case of a buck, we have a positive input, we have a positive output. It's a step down so that we get a gain up to 1. In the case of the buck boost, we have first of all a negative output voltage, and this is because when this transistor, which is the on or the on, is on, then we have a current going this way through this inductor, and then during the off duration, when this transistor is on and this one is off, then this current is continuing this way, and therefore we're going to get a negative output voltage. Not only that, we can get actually a gain lower or higher than 1 because the transfer function is minus, first of all, and then d on over d off. So when they are 0.5, it's 1. When d on is lower than 0.5, we have a step down, and when d on is larger than 0.5, we have a step up. So this is the buck boost, and this is the buck. Now, when you look at these two configurations, here comes the idea that for this, I'm showing here a synchronous configuration that is not just a diode, but a transistor to lower the losses here and here. So if you look here at the buck of this configuration, it turns out that you need the same thing here at the buck boost. So the idea is perhaps we can use this part here, actually the controller, to put it here so that it will actually convert it to a buck boost. So this is the idea we're going to discuss in this presentation. Now, the advantage is that in the original design, you do have to have two floating drivers, while here you have the driver built in. Of course, there is a problem of ground here, which I'm going to discuss, of course. So if I just take the buck and say, turn the 90 degree like this, I'm showing here now the power supply, then this is not sufficient, of course, because still ground is here and the output is here, so we don't have a negative voltage. However, if I move the ground from here to here, then we are definitely going to have here a negative voltage with respect to ground. As far as this circuit goes, everything is okay. That is, the circuit itself does not care what you call ground. You can put it here, can put it here, can put it in fact here. As long as there is one point which is ground, the circuit works in a regular way. Okay, so as far as the operation of the circuit, it is okay. But there is a point here that this is really not a buck boost. Because if you look at this circuit in which I've just moved the ground here, when this transistor, the D-on transistor, the T-on transistor is on, we see that we have the input voltage imposed on one side of the inductor, and then on the other side we have the output. So we have in series the input and the output. In a real buck boost, this is not the case. During the on period, only the input voltage is imposed on the inductor. So this is not really a buck boost. It is still a buck, but the operation will not be like a buck boost. There is another problem here, and that is that this power supply now is floating. So what did we do? We wanted a negative voltage, and now we need a floating power supply because none of its terminals is connected to ground. So we need a floating power supply, which if we have a floating power supply, we can have a negative voltage. So this doesn't make sense. So the next step is to move this power supply to here. And this is the configuration we are talking about. Okay, so what we have here is the basic circuit as it is, but we move the ground from here to here, and we move the power supply from here across to here. For those who might be a little bit confused with the 90 degree turn, I'm now plotting it in a sort of a regular way. You see the original circuit, and then rather than having the power supply here, I have added it here, and now I'm calling this point ground. So these are the two changes that have been made to the original circuit. Okay. Now this circuit now is not a buck converter. It's a buck boost converter, although in a different configuration. And we'll see what are the implications. but it is not a buck converter that is producing a negative voltage. It is a buck controller that is now operated as a buck boost converter. So now we see that indeed during the on time, and this is now the on transistor, T on time, we have the input voltage imposed on the inductor as it should be in a buck boost converter. Okay, so it's not like this. This is in the case of the buck converter, while here we have a buck boost converter the way it should be. But this change now makes a big difference as far as the total voltage across the controller. Originally, we have the input voltage. Now we have the input voltage plus the output voltage. Okay, this is the total voltage on the controller and the transistor. I'm showing here a case in which the voltage on the controller and the voltage on the switches are the same. Later on, I'll discuss a case in which you need two separate voltages to drive the controller and the switches. So in this case, we have the same voltage on the two, but now the voltage on the controller and on the half bridge, you might say, is not V in. It is V in plus V out with the absolute value here. Okay, so it's a larger output depending on the value of the output voltage. So it's altogether a different circuit even from the classical buck boost. So let's see some waveforms here. I've taken a analog devices controller. This is actually, this part here is from a jig as they call it. It's a reference design. I've changed the ground. This was the ground. I've changed it to here. And then I moved the power supply from here to here. So it is according to the changes that we have just made. I've also, aside from the load, constant load, I have added a load step here of 1 amp. Okay, just to see the response of this circuit. It would be recommended to put here a capacitor because this part, as we have seen, is not controlled by an input voltage. It is generated by the circuit itself. So it might be a good idea to put here a capacitor. I didn't do it for the simulation. It's okay, but it is advisable to do that. So here is an example of a simulation result. We see here the output. It is designed to be minus 1.8 volt. Here it is. This is the load step of 1 amp. We see the transient respond to this step. And then this is the total voltage. Now the input voltage here is 3 volt. This is minus 1.8 volt. So the total voltage here is 4.8 volt. And here is this, what we see here. This is the total volt. And of course we see here the transition because this voltage is not coming from a power supply. Part of it is coming from the 3 volt power supply, but actually part of it is coming from this voltage here. So this is why we have this transition. And as I've said, it might be a good idea to put a capacitor across the whole thing. Now to see the large signal and the small signal to respond, I'm now setting up an average model. And here is how I look at it. Now this circuit is basically going back a buck converter. We have an input voltage. Granted, it's not V in, but there is an input voltage. There is an output voltage. And the transfer function between the input to output is the duty cycle. Now, the average voltage here is the total voltage times the duty cycle. Okay? And this is the D on. So, this is the voltage, the average voltage, which is imposed here. And this is the idea of this average model. We have the inductor, we have the output section. I have added here some parasitic elements as an option for later on to see the effect of them on the transfer function. I'm not using it in this presentation. And here is the average voltage. This is the total voltage from in to out times the duty cycle. Now the duty cycle is just a generator here, a voltage source, and I am going to sweep it and to see the transfer function, that is what is the output voltage as a function of the duty cycle. And later on I'm going to run a small signal analysis, which is of course the advantage of this average model, that you can run a small signal analysis. And here is the large signal. What I've plotted here is V out over V in, okay? And this is now the duty cycle. Since this is the transfer function, a duty cycle of zero point 0.5, we should get a ratio of 1, and this is minus 1, as it should be. And then, of course, the voltage is going higher and higher as the duty cycle becomes larger than zero point 0.5, as I have said, but of course, it is a negative voltage at the output. And here's the simulation result for the small signal analysis. What we see here is that at low frequency, we have a phase reversal. It's 180 degrees, which makes sense because we have a negative output. And then we have a double pole here. It's going all the way to zero, about zero, and then it goes up again. Well, the reason for that is that LT spice has a hidden resistance in the inductor unless you make it zero, which I did not do. So there is a 1 milliohm here. So at high frequency, we are moving from the double pole to a single pole by the inductor and the resistor because the capacitor has already a very low impedance, and this explains this increase in the phase. Now, what about the case that you need two power supplies, one for the actual transistor for the switcher and one for the controller? There are some controllers like that need a lower power supply for the circuit itself, and then they do have a bootstrap for driving the upper transistor. Well, in this case, what can be done is to add here an LDO, and this will supply the voltage to the controller itself. With a bootstrap, you build up the voltage that you need for the upper transistor drive, so everything is the same except for the fact that you need an LDO to control the voltage of the controller. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much.